Hello and welcome to part 2 of our lecture video series for Monday, May 1st. I have decided to do a little change up in how I present these topics to you. So instead of looking at pressure, we're actually going to look at the kinetic molecular theory of gases first, because I think that understanding this theory or model of how gases behave is going to do a lot to help us understand pressure and its relationships to things like volume, quantity of moles, and temperature further down the line. So I think I'd rather start with kinetic molecular theory. So scrolling down to our notes, kinetic molecular theory of gases. So this is our intro to our conversation of gases. So if we're going to talk about gases, let's kind of remind ourselves about what on earth a gas is. So recall, we've got our 3 phases of matter, well, technically 4, but in this class 3, solid, liquid, and gas. And when we've talked about the gas phase, the way it's been introduced to you is that it's the highest energy phase of matter. Now that we know a little bit now, okay, so we know a little bit more now about what energy is, right? Like at least we know energy in terms of work or in terms of heat, right? So what on earth is this talking about when we say that a gas is the highest energy phase of matter, right? It's a little ambiguous. So let's begin by looking at the kinetic molecular theory of gases, or KMT. So all matter is composed of some molecules or atoms, depending on what we're looking at, and those are exhibiting constant motion, right? There's no system that has like a perfectly zero sense of motion, where this motion could be translational, like moving from one spot to another. It could be motion like vibrational, so you can imagine your bonds in your molecules acting like little springs. It can also be rotational, so if you have the ability to rotate atoms around their chemical bonds with one another, that's another form of motion. However, in the kinetic molecular theory of gases, we are assuming that gases are composed of particle-like molecules. And to you, that just means we don't have to worry about quantum mechanics. We could just imagine this being like little BB pellets or beads or billiard balls. And the assumptions that we make when talking about these little particle molecules are the following. So the first is that these particles travel in straight lines with some amount of kinetic energy. So they're moving at some speed in a straight line. And the only way to change their trajectory is by collision. So specifically collision, meaning running into something. This can be into other particles, or if we're thinking more practically, like what are we looking at this sample of gas in? We're looking at it in some kind of container. So we can look at collisions with whatever our container is. Okay, so when we talk about the highest energy phase of matter, we're assuming that all of these molecules are exhibiting, yes, vibrational and rotational movement, but there's a large degree of kinetic energy that is associated with our gas particles. Okay, so we've got these little molecules that are bouncing around with some kinetic energy. Another thing we assume is that the kinetic energy on average, AVG average, of each gas molecule is related to the temperature of the gas. We're going to talk about temperature relationships in a moment. But in general, if you're wondering, like, where does this kinetic energy come from that these gas molecules have, it comes from however much thermal energy is dispensed throughout the system. Okay. The third assumption we make in kinetic molecular theory is that collisions of gas particles are perfectly elastic collisions. So for those of us that are not in physics yet, there are two different ways in which things can smack into one another. There's a way called a elastic collision, which is where kinetic energy is conserved, meaning as a result of smacking into one another, the velocities and thus kinetic energies of those things that have run into one another do not change. And then there's inelastic, where kinetic energy is not conserved. That's all I'm going to say on that. If you want to talk about inelastic versus elastic collisions, come find me in office hours. So again, collisions of gas particles are perfectly elastic. This means that no kinetic energy is lost or transferred upon the collision. And I'm sorry if you hear some really loud noises outside. It appears my landlord has decided that right now is a great time to start hammering on the wall. Okay, let's see here. Another assumption of kinetic molecular theory is that gas particles have negligible volume compared to the space that they occupy. Meaning we don't have to think about how much space the molecules themselves take up, because in kinetic molecular theory, they are so small relative to the container that they are found within that it's okay to assume that their volume is zero. Now we know that that's not true, right? We have a mass, and due to density, we have some volume because we are matter. But in kinetic molecular theory, that kind of volume can be ignored. And I think, lastly, a really important one to consider, and we'll start thinking about this a little bit more in detail when we start talking about phase changes and then intermolecular forces coming up at the end of the year, is we assume that gas particles in kinetic molecular theory do not interact with one another besides colliding. Meaning there's no kind of like attractive or repulsive force that exists between our gas particles. There's no kind of like stickiness that's inherent to them. They're not going to cause or influence any change in one another. The only thing they're going to do is bounce off one another and then change trajectory. Not even their kinetic energy is going to be changed. So yeah, gas particles have negligible volume and they do not interact with one another beyond some kind of collision. So what does this look like? So I like to imagine what's going on with kinetic molecular theory by just, I don't know, thinking about some kind of container. So here we have this square, this is our container, and inside we've got some blue gas type particles. Let's call this gas 1. And then we've also got some red type gas particles. Let's call this gas 2. And you'll notice these are all in random motion. If you were to track kind of what's going on with one particle, you would see it's traveling in a straight line, and it only changes its trajectory if it bounces into another particle or into the sidewall here. And from this model, we would see that there's no change in kinetic energy of our particles, right? So it's not like as a result of smacking into one thing, we're going to have a change in the total kinetic energy that we possess, right? We have our initial kind of velocity maintained, or at least kinetic energy, I guess is technically not true. Kinetic energy maintained. And let's see here. Yeah. Anything else? Yeah, if I were to increase the temperature of the system, then my particles would have more available energy that they could convert into kinetic energy, which would affect their number of collisions. So in our next video, we're going to talk about how we measure properties of gases, and then also further down the line, how we relate gases. And it's all going to come back to how we think about gases according to kinetic molecular theory. So imagine just a little bit of chaos in your system when you're thinking about a gaseous system.